All right. Well, thank you for having me, Dan. Happy to be here. My name is Jeremiah. I'm the co-founder and CEO at Subspace Labs. Today I'm going to be talking about the Subspace network and our blockchain and its consensus protocol. It's really an honor to be here. I've been coming to these talks for almost 5 years now, I think, since the one Joseph Poon gave on the Plasma network. So it's nice that they're happening in person. And yeah, I'm excited to be here. So thank you. Okay, so this is the agenda for the talk today. I'm going to start by giving you a background and kind of a high-level overview of the motivation and the architecture for Subspace. And then I'm going to do a deep dive into the consensus protocol, starting from sort of the honest assumption of the way that it works in the happy path. And then we're going to go into attacks on the protocol and try to resolve all the attacks and show that the protocol is secure. And if we have some time, we'll get into the more interesting parts, the storage and the execution protocols. People tend to be more interested in those, but we have to understand consensus first. Okay, so to begin, Subspace it's a new blockchain. It's a Nakamoto consensus style blockchain, longest chain protocol, and there's a few main flavors of. That's not showing up there. So a few main flavors of Nakamoto consensus. So of course, proof of work, very simple, very secure, uses a lot of energy, electricity, trends toward centralization. Proof of stake is attempt to solve the energy problem, but it's more complex, has more security problems, more challenges, and it tends to be more permissioned, or it reduces the sort of dynamic availability property that Bitcoin has. And proof of capacity is the idea of one disk, one vote, or sometimes called proof of space, or proof of storage, or proof of replication, or proof of space-time. It's the idea that you can kind of get the best of both worlds. You can have a permissionless protocol like Bitcoin, and it can be more open, but it can use less energy, like proof of stake. And there's many different variations of proof of capacity. But this is kind of what inspired me and my co-founder to get into blockchain originally, sort of the vision of proof of capacity blockchains. But there's some incentive challenges with proof of capacity consensus that we identified and that we kind of set out to solve. Just for a little bit of background, it's one thing to have a protocol. It's another thing to build an implementation of the protocol and to see how that works in practice. And when you run nodes on these blockchain networks, there's some resources that you have to dedicate to the network, some storage and some compute resources, and it depends on what kind of node you run and what kind of security properties you want to get from that type of node. The point here is that when you run a node, a full node or an archival node of a blockchain network, that there's the storage, and this is kind of the cost you pay to run in a secure way and to really be a good participant in the protocol. And these numbers for Chi are kind of not perfect, so don't quote me on those, but that was what we were able to estimate. So the problem, the core problem that we saw was that if storage is the thing that you're pledging to the network, to get a reward. So if you're running a farmer, a consensus node in one of these proof of capacity blockchains, then you're basically penalized for being a good node. So if you actually store the history and you maintain the state, that this space is going to count against your plot. The bigger your plot, the more your reward. So if you want to be a rational node, or if we assume that most people that are running those in these networks are actually trying to make money, then they're going to do what they can to get the highest return on investment that they can. So they're going to discard. They're going to ignore the history, so nobody can sync from them. So we need some centralized archival service to sync the network. They're going to discard the state, so they can't verify the new blocks. And then effectively, they become a light client in the best case. In the worst case, or in the average case, they probably end up joining farming pool. But they get more reward per unit space that they pledge to the network. So this is sort of a concern that these proof of capacity networks, they actually trend towards centralization much faster than proof of work or proof of stake networks, because there's actually a penalty for being a good node, whereas it's just kind of an overhead that you have to pay in proof of work or proof of stake networks.
Do we know what happens on the chain of work in practice?
Yeah, actually, for Filecoin and for Chia, I mean, they're different because they have different principles, but I guess for Chia, actually there was a trend towards towards pooled farming for a different reason. It was actually because of the reward frequency that showed itself sooner, because you would pledge 10 terabytes of space, and I think it takes you something like 4 years right now to mine a block or to farm a block on Chia. So that's another problem. And we kind of resolved that in our protocol too. We have more frequent rewards. But there's, the problem that's one of the reasons, I guess, that people want to join the network, is because they can get more, it's easier, I guess. Okay, so this is kind of a high-level architecture of our protocol, and really an outline for the technical white paper that we wrote. And there's really 3 parts. There's 3 key ideas. So the first is we want to incentivize nodes to store the history. So basically, we try to make the history and the plot the same thing. The second is and so we call that proof of archival storage consensus. So it's basically proving that you're storing the history of the blockchain. We do a decoupling of consensus and computation, which is not a new idea, but we do it for a different reason. So we actually make it so we have a second class of nodes. We call them executors, and they maintain the state and do the state transitions. You can almost think of them like operators in a farming pool or a mining pool, but they are sort of staked and accountable operators. And then we actually construct the network in such a way that the farmers form the sort of distributed storage network, kind of like BitTorrent in a way. It's one way to think about it. So that as we get more nodes on the network, the storage capacity of the network grows, and we can get more and more utility out of the network. So we're really going to look at the top part here, how the proof of archival storage consensus works. Before we get into that, just to say a little bit about us. So we've written most of the code. We actually have an implementation. We have a live network. We have over 20,000 nodes on our network right now. We're actually preparing to launch an incentivized test network soon. That was just to show that we're a substrate-based chain, so we're in the .sum ecosystem. We're not a parachain, but we actually had to run our own telemetry server because they wouldn't let us show how many nodes we had on our network. This storage is actually being used right now. We're actually backing up we're archiving all of the blockchains, all the parachains and the relay chain in the Polkadot and Kusama ecosystem. And we're planning to eventually do this for Ethereum. That's what we're going to do next. And then for other chains, other ecosystems, and that we can use this archiving as a way to sort of build a bridging protocol or a cross-chain messaging protocol, because we're actually validating this data as it's coming in as well. So it's kind of a one-sided bridge right now. This is just one example. Really, we can store any data on the network. This is just one use case which we've been focused on. Okay, so now I want to talk about the consensus layer a little bit. And in our protocol, the consensus layer is mainly just a way to agree on the ordering of transactions. It's not a way to execute the transaction. So that's this decoupling that we do. So the farmers in our protocol, they really just treat the blocks as data. That's what they see it as.
Sorry, so this chain is like a data storage chain? It's like a Celestia type system, or does it actually execute?
It does execute, yeah. We just have a second set of nodes that do that execution. So I guess I probably should have talked a little bit about that, but we have we have this concept of 2 kinds of nodes, because we don't want the farmers to store the state, because they're not gonna want to do it. So we allow these other nodes, we call them executors, to stake, store the state, get elected to process the blocks, to execute the blocks. They maintain the state, and then they commit back to this state. And then we use an optimistic fraud-proof system to make sure that that's correct, basically. So it's still, it's kind of like Ethereum-style at a high level. Like there's still a notion of like generic execution. You can have any virtual machine you want inside of it. We just do that in such a way that the farmers don't have to mess with it, but they have better security properties than a light client, because they can just check the fraud proofs or be sure that the state is correct.
So on this slide, I'm assuming the farmers are doing 1 and 3 by the color coding.
That's right.
And I guess my question is, intuitively to me, the staked executors would be the one proposing the blocks. Are you going to talk about why the farmers are proposing the blocks later? Is that jumping ahead?
Yeah, I can talk about that right now. Well, the farmers are proposing the blocks because we want the control of the network, the sort of consensus layer control, to be in the hands of the farmers, like to be in the hands of the community, or sort of the people, I guess you could say, versus like the wealthy, which is like the proof of stake. So that's sort of like, I guess you say like a philosophical point of view in our protocol is we want like more people to be in control versus like, investors or whales or whoever has the coins. So the technically, like if we were to really unpack this, the executors do have some say. They can censor transactions to some extent, but not in sort of the Nakamoto sense where like once they get 51%, they can censor everything. Like if they had 90% of the stake, they could censor, it would just take longer to get an honest transaction included in the chain. But the farmers are ultimately going to order the transactions. They're going to sequence them as a way to sort of get away from MEV. And they, and they make sure that the transactions eventually do get included in the chain. Cool. Okay. So to step back. Yeah. So for the consensus layer, so this is the consensus model at a high level. So this is a proof of archival storage consensus. It's a two-phase protocol, like most proof of space or proof of capacity protocols. So there's an initial setup phase where you actually create your plot. The plot is the history of the blockchain itself. So one way to think about this is if you imagine you have a Bitcoin blockchain and you store the full history like an archival node of Bitcoin, which most Bitcoin miners do or nodes do because it's only about 400 gigabytes right now. Imagine instead of storing that canonical history, you stored some uniquely encoded history that was provably unique. So basically use like AES and encoded it with your public key, for example. And so everybody on the network is going to store these unique copies of the history. And this encoding is going to take some time and some energy. And then what we're going to do is instead of querying, instead of doing some kind of a hash puzzle to solve the next block, we're going to audit this storage to see if people are actually storing. And if they are, if they meet some challenge threshold, they're going to be able to produce a new block. All right.
So this is similar to like or going down the path of a proof of replication type scheme.
Exactly.
Okay.
Yeah. Okay, so I lied. There's actually an initial step before the setup or before the plotting phase, which is the archiving phase. So we actually have to prepare the history. This is so that we can have the property, like the robust properties of the distributed storage network that we want. But what we're actually going to do is we're going to take the blocks and we're just going to add them. You can just imagine like adding them into a buffer. Right now it's about 512K. And then once that buffer gets full, you slice it into these constant size pieces, which are 4 kilobytes. And then you're going to erase your code a parity set. So right now it's an equal parity set. Then you're going to build a Merkle tree over all these pieces. And then you're going to take that root. That root is going to go into a table you're going to use to authenticate that pieces are part of the history of the blockchain. And you're going to take the witnesses and you're going to actually concatenate them to the records. And that's the pieces that farmers are going to store. So basically the pieces are self-verifiable as long as you have this these roots, or we call it the root table. Okay, so this is how we prepare the blockchain. So we basically double the size of the blockchain in order to do this. And now that we've got these pieces, we can encode them. So the encoding function we use right now is sloth, sloth 256189, which just means 2 to the 256 minus 189. So the highest prime that we can get. And to be accurate, it's not actually sloth, it's the modular square root puzzle internal to sloth that we're using. And we do this, it has this property that it's slow to encode, but it's very fast to decode. And we expect that there's going to be lots and lots of people, lots and lots of nodes decoding this. So we want it to be as efficient as possible.
Are you using the same thing as the EF is doing, also the pasta curves, or is this what curve are you using?
It's not a curve, I don't think. It's just a prime.
Sorry, which prime are you using?
2 to the 256 minus 189.
Oh, I see.
Yeah.
It's not.
Yeah.
I see.
Is that the one that Stark
So.
using?
So, I mean, the interesting thing is the Ethereum Foundation is developing hardware specifically for the pasta primes.
Yeah.
So you might want to, you're probably going to migrate to the pasta primes eventually.
We had actually looked at that. So we're actually working with Supranational to do basic analysis on this, actually. So we had actually talked about that and explored that.
Makes sense. Yeah.
But yeah, it's a great point. So yeah, so we take these pieces, we create these encodings, and really sloth is just an optimization. You can think of any pseudorandom permutation working just as long as we get the property that the encoding is indistinguishable from random data. then it technically is a proof of replication. Once we have the encoding, the encoding key is the hash of the public key or the node identity of the farmer. So the plot is cryptographically linked to the identity of the farmer who creates it, but in a permissionless way. So once we have the encoding, we're going to create a commitment to the encoding. We call that the tag. You can just think of hashing it right now. And we're going to write the encoding to disk. That's the plot. And then we're going to write the tag to a binary search tree. So this is like a lookup table, which allows us to do very efficient, very fast queries to the BST. Right now, the BST is like 1% the size of the plot itself. Okay, so this is the plotting phase. So now we go into the farming phase. So this is the sort of the challenge response or the audit, or what we're going to build Nakamoto consensus from. So right now, just assume that we have some kind of proof of stake like time slot based system, and we have some secure randomness beacon. We'll return to that later. So let's say we have a secure challenge, random challenge, which is coming out. What we're going to do is we're going to query the BST, the binary search tree, for the nearest tag to the challenge by XOR distance. So you can imagine if you took a ring over the domain of the hash function, and you put all the tags on the ring. At each challenge, you're basically picking a random location on the ring, and you're trying to find some the tag which falls within some small sector of that ring, and you just tune the difficulty or the size of that sector such that on average you get one every 6 seconds or one block every 6 seconds in our protocol. Okay, if you do find a tag which satisfies the threshold, so that would be like on the whole network, there would be one tag every 6 challenges. It's challenges once every second right now. Then you would pull out the tag. It would reference the encoding. You'd read the encoding from your plot, and you would generate this proof of replication. You'd also sign it to show that it's linked to the identity, prove the ownership of the key, and then you distribute this to the network. And everybody can very easily verify this. They just run the decode algorithm using the public key. It's about 1,000 times faster than the encode. And once they decode the piece, or once they decode the encoding, they get a piece. The piece has the witness embedded within it, so then they can verify that it does actually correspond to the canonical history of the blockchain just by having this very small root table. And they check the signature, and it's a valid POR. And then we can use this as the basis for producing a new block.
So what happens if you end up with 2 people producing these proofs?
You can have forks, so it's probabilistic. So just like proof of work, you can have 2 people, or like Ouroboros-Prowse, you can have two different nodes that get elected at the same time. So then you just have an honest fork, basically. Just same as Nakamoto consensus. They both get broadcast to the network, and yeah. Okay, so that's the.
Sorry. And if 0 people get elected, then the chain is stuck for a little bit.
Then you just move on to the next slot. Mm-hmm. So yeah, so actually it might be easier if I show this diagram here. So basically you've got this clock. It's just ticking at some constant rate. Every slot you get a new slot challenge. And actually it's expected that in most slots there will be no solution, and you just keep going until you find a solution, which on average is about every 6 slots. Okay. Okay, so yeah, there's some other proof of capacity protocols, blockchains out there. How are we different? We get asked this a lot. So there's 2 broad categories we can use to distinguish them. So we have some protocols which are what we call a proof of space. Technically, it's all a proof of space, but they're just a proof of space. And they're just wasting space intentionally, just like Bitcoin wastes computation. So BGN space mesh. And then there are proof of storage protocols where you're actually, the data that you're storing is some useful data. You just make it look like random data using some kind of pseudorandom permutation. That's where the proof of replication comes from. So in our case, we're permanent archival storage. In something like Filecoin, it's temporary storage. So something more like Amazon S3, where you're sort of paying by the month or paying by the quarter. In our case, we're more like something like an Arweave or like an Amazon Glacier, where you're just paying once and you're kind of assuming the data will be there more or less forever. And then there's this other distinction between these permissioned or permissionless protocols. You can think of permissionless more like proof of work, where you can just kind of come and go. There's no registration, there's no authentication table. And in a permission protocol, it's more like proof of stake. And so we're trying to be as permissionless, as open as possible, as low barriers to entry as possible, but also having some utility out of the storage at the same time. Okay, so that's the honest protocol, but that's actually not secure. There's lots of ways that you can attack that protocol. And what we had to spend a lot of time doing is trying to figure out how to actually resolve these attacks. And Srivatsan actually helped us with some of these last summer. Okay, so to start out with kind of our assumptions and what the model is. There's this paper that Tal Moran wrote, who was one of the founders or creators of the Space Mesh protocol, about rational proofs of storage. And so, a lot of times in cryptography and in blockchain, we have this notion of like absolute security. And this is kind of an argument that you don't always need absolute security. Sometimes you just need rational security. If we think of we're in sort of a network where everybody's playing like an economic game. And so this was an interesting idea. And we tried to kind of expand this into our protocol. We thought this made a lot of sense. So kind of our basic assumptions, so we are Nakamoto consensus. We want to have this 51% honest majority assumption, like it's secure in terms of safety and liveness, as long as 51% of the participants are following the protocol. And what we say is that if 51% of the resources, and you could just think of that broadly as economic resources or like capital dedicated to the system, is controlled by economically rational nodes, then they're going to use it to store data to pledge space to the network, because that's going to be the most rational way to participate in the protocol. That's where you're going to get the best return on investment. And then if that's the case, then it will maintain safety and liveness, and it will also maintain fairness. By fairness, we mean that you couldn't basically like mine or use a GPU to generate proofs of replication on demand, as opposed to just pledging space to the network. That's always going to be the best strategy. So that's kind of the goal that we have against all of these many, many attacks that there are on this construction. Okay, so this is a sketch of what we're going to do. So the first problem is we actually need to make sure that the proof of storage or the proof of replication underlying it is secure. The plotting basically is secure. Once that's good, then we need to make sure that our randomness beacon is actually secure, that our blockchain is secure, the chain structure is, we can maintain the integrity. And then we also have to deal with this problem of time that we have in all efficient protocols like proof of stake and proof of capacity, and how we're going to deal with all the sort of other challenges that come up. And we do that in kind of a unique way.
So actually, in Filecoin, it's a fairly heavyweight mechanism to ensure secure proof of replication and all that. And that they needed that because of the useful data, which you're also doing. So how is it that their mechanism is so heavyweight and your mechanism is so lightweight?
That's a great question. Yeah, so it's a different notion of useful storage. So in Filecoin, the blockchain is used basically just to hold smart contracts and to audit smart contracts for some off-chain storage. And that off-chain storage could be kind of any arbitrary data that could be sent to the storage nodes, like in any kind of order, basically. So it's a huge sort of problem, like a huge sort of attack surface to think about. In our case, we sort of constrain that problem to just storing the history of the blockchain, which we have a lot of control over the way that data gets formatted and sort of how big the data can be. But we can extend that to make a useful storage protocol by basically the same way you can store data on Bitcoin or Ethereum, like an OP return or the call data, and just make that more ergonomic and kind of design the transactions around the ability to write data into the blockchain.
So in principle, Filecoin could do what you're doing to achieve their goals too?
It's a good question. I don't think so, because their consensus is really kind of a combination of like proof of work, proof of stake, and proof of replication all wrapped into one. So I think it would be some major changes to their protocol if they tried to do something like this. But perhaps I really haven't thought about that.
And then while we're on this topic, sort of related, because of the time windows you were showing earlier, that's what's going to control the amount of latency I can do on the storage, right? Because it's that once a minute that I have to supply the proof. Because once I've got my key selected, then I have to respond fairly quickly. So like the thought of the attack here is I get a tape drive, right? But that takes hours to pull the storage back. And that's how you solve for that, right?
Sort of. So there's a difference between like using the blockchain to retain or to like retrieve some useful data and like using it as a way to audit consensus.
Yes.
So those are actually kind of two separate ideas in our protocol. But to the point of tape drives, actually, you couldn't use a tape drive in our network. There's actually a couple different reasons for that. It'll make sense when I go into an attack, but it's a good question.
You need random access, right?
You need random access.
Yeah.
Yeah, absolutely.
Random access, not on the span of hours.
Yeah.
Exactly.
We actually did some analysis. We thought there might be some kind of efficient attack you could do with a tape drive, but it turns out it's pretty hard to do. Okay. Where are we at? All right. Okay, so starting with sort of the simplest attack you can do, we call this lazy farming. So this is kind of breaking the notion of actually doing useful storage. So we're saying that the honest node on the left, they're basically going to download the full history of the blockchain, and they're going to create this one unique replica of the blockchain. But actually, there's nothing to prevent a node in the protocol from just taking one piece and just generating lots of different node identities as the encoding keys, and just storing that one piece millions and billions of times. And what are they doing? They're saving a little bit of bandwidth. So maybe it's really not a big deal. It turns out that you can use this attack to construct more sophisticated attacks, and it actually is a big deal. So we want to prevent this. So the way that we prevent this is we actually salt the challenge with the node identity. So basically every node on the network has a local challenge that it derives from the global challenge. And that means that for each binary search tree they have, or basically for every set of pieces they have, they would need a unique binary search tree. And so they have to query all of those binary search trees every time there's a challenge. So basically, the degree of like Sybil farming that you do increases the computational overhead of just participating in the network linear in that amount. So you could probably still have like a small constant number of BSDs or plots, but it's not really going to make sense to just do that in mass. That makes sense?
Well, what if you largely exceeds the data that you need to store, right? You have like nodes capable of storing 1 billion times whatever is needed for your network, right?
They can, that's fine.
Then you can reuse storage. Right?
Yeah, absolutely. And that's fine. But so we actually have a notion of a max plot size in the protocol, which is 100 gigabytes right now. So there is an assumption that you are going to do some Sybil farming, like the total space you have divided by 100 gigabytes. We just don't want people to be doing like 1 megabyte at a time per identity. Okay, so the next thing you can do, it's kind of a simple, straightforward way to think about it, is you can just mine the proofs of archival storage on demand. So the honest farmer has created this plot, they've written it to disk, they've got the BST on disk. When there's a challenge, they query the BST. There's nothing to stop you from just encoding like with no disk, and just once you see a challenge, there's some window when that challenge is still available to produce a solution. It's about a second that you have right now. And you could just encode as many pieces as you want within 1 second, or within the challenge interval, the challenge window. And you have some probability that you're going to get some solution. But to have the same probability of getting the solution as the honest farmer, you basically have to encode within like 1 second as many as they've encoded in 24 hours. So it requires a lot of parallel computation to do this. So we've looked into doing this with a CPU, doing it with a GPU. We've actually done ASIC design for this as well. We actually have an assembly implementation of Sloth 256189 that's basically optimal on x86. We also have like a CUDA and a PTX and OpenCL implementation for the GPU, which is basically optimal as well. So we have a pretty good idea of what's possible with the existing hardware, and we've already started doing some conceptual design for ASICs, and we're starting to get an idea of what's possible for that. And the realization is that we can just sort of tune the encoding delay, which what that really means is the number of layers of encoding that we do, because effectively what we do is like AES CBC mode, but we just replace AES with Sloth in our permutation, and we can just chain those together and do like multiple layers of that, and that's what we consider the encoding delay. And so the idea is that while you could do this, there's going to be a continuous electricity overhead cost of doing this, and we just tune it such that it's always cheaper just to have the honest storage. just to do it once, basically.
Wait, isn't at some point the ASIC is just not gonna be fast enough to respond quickly enough?
Well, you can just have more ASICs. So one ASIC won't, but you could just parallelize, because the plotting itself is parallelizable. One single piece is sequential, but you could create as many different pieces in parallel as you want.
And there was no way to make the sequential part just be long enough, longer than a second?
There is, but then if you do that for one single piece, then it leads to very, very long encode times for plots. And if you chain the pieces together, then it starts making the proof sizes better. There's probably more advanced ways to do this, probably using zero knowledge proofs, so that you could have like multiple pieces chained together and have like a ZK proof. And you know, that's the road Filecoin went down, and we wanted to try to avoid that because we didn't want to have a notion that you need to have like a GPU or some special CPU just to generate the proofs or to verify the proofs, or not to verify, but you know, there's like a special way you have to plot so that these proofs can be constructed. Then even once you create, like once you get the challenge, you have to like generate the proof. So it adds a lot of complexity. We're just trying to avoid that and go with the simplest scheme as possible.
But then isn't it the case that like as say if I go to a place where power is cheap and you know as ASICs get faster, you're gonna have to retune your chain?
Yes, so that's kind of the analysis we're doing. Like if you go to the place where the electricity is the cheapest and like what is probably, you know, using current process or even estimating the process, what that's going to be. So we're pretty sure that we're secure against this attack, like within good margin. There's actually another attack that we're more concerned about with the ASIC. It gets worse.
But on this attack, I just want to offer too that like processing is getting cheaper at a much faster rate than the storage is, right? So to your comment about retuning the network, but I think it's fine because you can just add more cycles. You don't have to revise the history of the chain. So I think that works.
That's right. You can always just add more layers and increase the encoding on the existing plots. So yeah, we can retune the network over time. We can make it more secure. Actually, what we expect is that we might even be able to decrease the security of the network because we'll have so much storage that it will just be even less economical to do the ASIC attack over time. But it'll be interesting to see how that plays out. Okay, so there's a more efficient form of this attack. We call it the compression attack. So again, the honest farmer creates its plot, it creates its BST. But when it's solving on the challenge, it actually only needs the BST to solve the challenge. Now, once it finds the piece that it needs, it can regenerate the encoding for that piece fairly quickly. So it could just have one canonical copy of the blockchain, or several nodes could just share one canonical copy of the blockchain and just store lots and lots of BSTs, and then just generate rarely when they need it, encoding that can generate that on demand. And if the BST is about 8 gigabytes, you get something like a 125x compression factor. So this is bad, of course. And how do we deal with this? So what we do is we make it so that these BSTs are actually periodically committed to. So you have to salt the BST. So whenever you create the tag, you actually salt it with some on-chain randomness, like based on some epoch within the blockchain. And so you make it so that, once every 2 weeks, you have to read your disk, recommit to your BST, and then you can move on and solve from there. And this is actually kind of similar to the way Space Mesh works. This was another idea that they had in their protocol. This is how they're able to achieve that rational security, is by playing with this interval. And this is something you can actually really easily adjust over time. It doesn't require any change to the plotting or the layers or anything like that. You can make it so that, as there's more storage on the network and it's harder to do this attack, that you can even make this period longer over time. Yeah, so that's how we deal with the compression attack. But the computation, the calculation about what the correct recommitment interval is very dependent on what an ASIC could do. That's like the worst attack that you have to consider when you think about this. So that's what we're currently doing right now. Oh, actually, I think someone's talking and I have my computer muted. Sorry. Was there a question? Oh, okay. Okay, so assuming that we have a secure proof of replication built into the protocol, we still have to make sure that the randomness beacon is secure and that the chain is secure. And so This is a well-studied problem in proof of stake and other proof of capacity networks. And there's just some basic standard solutions for dealing with this. So the first is you just have to separate the proofs and the content. So you can't just malleate on the content of the block in order to try to influence the challenge. So that's pretty straightforward. We just segregate the two data sets. You can also equivocate. So if you see a fork in the network, you can solve on both branches of the fork. And then you could potentially build on both branches of the fork. So this is not good for security. And in proof of stake, it's actually very easy to punish this because you can just slash people that do this. But in our case, we're a permissionless protocol, so there's no deposit to slash, but we do have these plots, and these plots are cryptographically linked to identities. So we can actually add those to a block list. And we can basically prevent them from ever farming with that plot again. And so that prevents public simulation. And this is also known as the nothing at stake attack, typically in proof of stake protocols. But in the private simulation case, doing a private attack and trying to simulate, so like building a large tree to do this, the standard solution of this is, instead of making the challenge based on the last block, that you just take some set of last blocks, and then you derive a challenge from that, and then you reuse that over many blocks, over called challenge recycling. So I think it was Ouroboros-Prowse that really formalized this process. And that way, basically, the more you reuse the challenge, the harder it is, the less advantage you get from the simulation, but also the more predictability you get in the protocol. And so the actual protocol we're using is something called C correlation, which David Say created with some of his students. He's one of our advisors. So C correlation is the idea that if you go back and you just count the proofs, like basically every 256 proofs, you take that proof, you take the hash of the proof, which is canonical, and use that as the input to the challenge for the next period. And so for the next 256 blocks, that's what you use, and you just keep doing it. So it's same idea, it's just simpler, basically. And so what you wind up with at about 256 blocks, or every 256 blocks, you change the randomness beacon. It's about 26 minutes of predictability. So you can look ahead into the future about 26 minutes and know if you're gonna farm the block. And at that point, you don't get full 51% security, you only get about 47%. And this prediction window is bad because you can have bribery attacks, because you can basically offer people to produce invalid blocks or blocks that present some kind of a fork. And it actually makes the on-demand encoding attack worse as well, because instead of having 1 second to execute the on-demand encoding attack, I have 26 minutes to do it. So that can be much, much worse, especially when you think, well, what if like Ethermine or some GPU mining farm or NiceHash or something like that were to take that 26 minutes to attack the network. That could be pretty bad. So we need to figure out how to get rid of this. And then, of course, we also have the good old long-range attack, or the history writing attack, which proof of stake and proof of capacity all suffer from. In proof of capacity, the idea is that you have some amount, and thanks, David, for letting me borrow this slide. This is from a proof of stake presentation he gave. You have some amount of storage on the network that's honest, and then you have some huge jump in the storage on the network. So like right now, we're launching our incentivized testnet, so we're getting like a huge jump in users. And what you can do is even with just a small fraction of that storage after the jump, as long as it's more than the average amount of storage before the jump, then you can just go back and you can produce effectively a heavier chain from Genesis. Now, we had thought that this was actually hard to do in our protocol because the plots are linked to the history, and that you would have to not only recreate the chain, but you'd have to recreate the plots and recreate all of this storage in order to actually carry this attack out. But it turns out that there are efficient ways to do this so that it's not as cheap as proof of stake, but it's still computationally feasible to do it. So even proofs of archival storage are susceptible to this attack, and we need to resolve that as well. And so we do have a proof of time in our protocol as well. It's a different construction. It's simpler, and we're trying to decouple it as much as possible. So we kind of layered on, or added on as an additional layer on top to what we're doing. So it's similar to something like, I think it's called a proof of elapsed time, like what Solana uses, where you just have like a simple hash function that you're iterating over and over again. We use a permutation, we use AES, and we do this over the random beacon. So we have some randomness generation protocol that's the input into the proof of time. We iterate over that. We periodically commit the history back into that as well. So we're sort of sealing the history. And then we use this output of this iterated permutation as the input to the randomness beacon. So you really can't know what the challenge is until basically right when the time slot arrives, or just before the time slot arrives. So this idea was kind of inspired by another paper David wrote called Proof of Stake Error of Time. In that paper, it assumes that all the nodes are running this iterated hash function because they have to generate the challenge. We don't want that because we want the farming to be lightweight and not use computation. So since we have these two classes of nodes, we have the executors and we have the farmers, we can actually let the executors run this. They can sort of broadcast this randomness beacon, and we can use the fraud proof system so that the farmers don't have to verify it. They can optimistically trust it, and then anyone can show, if there was an incorrect transition of the proof of time, they can just generate a fraud proof to show that. So this can be very, very lightweight to do this from the point of view of the farmers.
So the executors also have to have special hardware to run as fast as they can.
Yeah, so that's another thing that we looked at with Supranational, is how fast we could speed up AES. It's actually not that bad. So it looks like maybe between 2 to 3x over, because I mean, AES and I has been 20 years, they've been optimizing that. So we're going to start with AES and I on like high-end machines. And then we're actually going to, we're setting up a foundation, and the foundation is going to be funding development of these ASICs. And we're going to probably do 2 generations of AES proof of time ASICs. Similar to kind of like the VDF competition that Ethereum did. Yeah, so this gets rid of the long range attack, or it makes it much, much harder, because the A max that you can get is only about 2 to 3x, assuming that you have this ASIC, and we're going to do that anyways. The prediction window becomes much shorter. It's actually shorter than it was before. So now it's just like even less than a second if we want. One thing that's unique about this is we don't have difficulty resets. So in something like Chia, you have a proof of space and a proof of time, but they both have difficulty resets. So they have the assumption that when the better hardware comes out, it will just automatically readjust itself. In our case, we're planning to do this just through soft forks. And it should only happen a few times in the life of the network. So what this means is that if you get a speed up on the proof of time, like if you do generate one of these ASICs, the worst thing you can do is a long range attack. You can't actually appear to have more storage just because you're generating the proofs of time faster. Yeah, and that's basically it. So yeah, this is the end. I think I know we're over time, so I'll stop here. Yeah, basically, what this comes down to is we believe it is secure, economically secure, as long as we have the proper security parameters. And so we're in the process of parameterizing it right now based on this analysis of hardware analysis, basically.